Now let's talk about the conservation laws that are applicable to elementary particles. And, uh, and we have conservation laws in classical physics. We have the conservation of charge, we have the conservation of energy, we have the conservation of linear momentum, we have the conservation of angular momentum. And in addition to these conservations, that we must have those conservation laws should hold for elementary particles. And in addition to these conservation laws, we have the additional conservation laws. And what are they? They are, say, law of conservation of lepton number. So, in a reaction, in addition to have the basic conservations in charge, conservation in energy, linear momentum, and angular momentum, in elementary particles, we must have the law of conservation of lepton number must hold, and law of conservation of baryon number must hold, and a law of conservation of isospin that we have already discussed, symbolized as I, should hold. And the law of conservation of third component must hold. So third component of this isospin, what is symbolized as I3, it must hold. And law of conservation of hypercharge, charm, and bottom quantum numbers should hold. Now, let us start with the law of conservation of charge here. If we talk about the conservation of charge, law of conservation of charge. Now, according to this law, the total charge of a particle or a composite system before it decays, it must be equal to the total charge after its decay. That means if you have something, it has a charge, say it has a charge A, it will decay into some capital B and some capital C and some capital D. The overall charge of the products that we have here must be equal to A. Now, this law of conservation of charge, what it does basically, it explains the stability of an isolated atom. Stability of an isolated atom. And stability of an electron. I mean, in other words, electrons cannot decay because of the law of conservation of charge. They will not decay because of the law of conservation of charge. Now, if I take an example, suppose I have an electron and I choose that it decays into a neutrino and a gamma ray photon. Let us assume that we have something like this. Now, this kind of decay is forbidden. This kind of decay will not take place. Now, why it will not take place? We can see that this electron is the lightest particle, and it can decay only into the particles which are lighter than the electron. So the energy can be conserved. And in the given decay charge, we can see that charge is not conserved. And hence, this electron cannot decay. Or I should say that an isolated electron is a stable thing. It's stable. And why it is stable? It is stable because of conservation of charge. Right. Now, the next thing is conservation of lepton number. We have already talked about leptons. Now, according to this law, in a given decay or in a given reaction, the total lepton number is conserved. Now, let us take an example of mu negative, and suppose it decays into an electron and a neutrino and an antineutrino. Now, let's go with the lepton number here. Now, what is the lepton number? Now, for this, we have the lepton number 1. And for electron, we have the lepton number 1. And for mu neutrino, we have the lepton number +1. And for the antineutrino, we have the lepton number -1. So we can see here that the lepton number is conserved, because in the left-hand side, the lepton number is +1, and in the right-hand side, the overall lepton number is +1. Now, talking about the charge, here we have charge -1. Here we have charge -1. Here we don't have any charge. Here we don't have any charge. So we can see here that the charge is conserved. So both lepton number as well as charge, if I quote it as a charge, they are conserved. So this is a possible reaction. It's not a forbidden decay. This decay is possible. Now, similarly, if I take another decay process of, say, mu positive as E positive plus nu E plus nu mu bar. Now, lepton number, okay. Now, for this mu plus, the lepton number is -1. For this E plus, the lepton number is -1. For this nu E, the lepton number is +1. For this nu mu bar, the lepton number is -1. And talking about charge, so charge we have +1. Here we have charge +1. We don't have any charge. We don't have any charge. So in this decay also we can see that both lepton number and charge, they are conserved. Now, what is important here is that it may be noted that a single lepton is, it's never created or annihilated. I mean, for example, if I have a gamma ray photon, it gives me electron and positron. It's allowed, as the lepton number in this case is conserved. But if I think of gamma ray photon giving me an electron and a proton, now this is not allowed. It's forbidden. This is forbidden and this is allowed. And why it is forbidden? Because we can see that the lepton number is not conserved here. Now, let's go with the law of conservation of baryon number. Law of conservation of baryon number. B. Okay. Now, according to this law, what we have is, in every reaction or a decay that we have, baryon number must be conserved. Now, say for example, if I take a neutron, it gives me a proton, it gives me an electron, and it gives me an antineutrino. Now, what is the baryon number here? Here I have +1, and here I have +1, here I have 0, here I have 0. Now, since the baryon number before the decay is equal to the baryon number after the decay, hence I will say here that sigma baryon number is constant. So the baryon number is conserved here. Now let's take another example. Say for example, if I take an example of a proton showing it as E positive and gamma ray photon. Now let us see whether this decay process is possible or it is not possible. Now what we can infer here is that what about the baryon number here? We have +1 for the proton. for positron it is 0, for the gamma ray photon it is 0. So we can see here that this baryon number is not conserved. So if baryon number is not conserved, then this reaction is not possible. This decay process is not possible. You cannot have a proton that can decay into a positron and a gamma ray photon. And this is because the baryon number before the decay is not equal to the baryon number after the decay. Hence, the given decay is not possible. Now, from this forbidden decay, what we conclude? We conclude that this proton cannot decay, and hence proton is a stable particle. It's a stable particle. Now, let's take another example. Take some examples where we can have a set of situations where we can check the conservation of this baryon number. Now, let me take the first one as say, for example, proton plus neutron, giving me proton plus neutron plus pi neutral. Now, what is the baryon number before this decay? Here we have +1, here we have +1. And after we have +1, we have +1, and here we have 0. So we can see that the baryon number is conserved. Baryon number is conserved. Now, if baryon number is conserved, therefore the given reaction occurs in nature. It occurs in nature. Now, let's take another example. Suppose we have proton and neutron. It decays into proton, neutron, and a gamma ray photon. Now, the baryon number +1, the baryon number +1, so it's giving us 2. Here I have +1, here I have +1, and here I have 0. So again, in this reaction, what we see that the baryon number is conserved. So this reaction is possible. A proton and neutron can give us a proton and neutron and a gamma ray photon. Now, let's take another example. Say, let's take another example. Proton plus neutron giving proton plus pi negative. Now, the baryon number +1, the baryon number +1, so it's 2. So the baryon number +1, the baryon number +1, and the baryon number 0. So the baryon number is conserved. Now, this reaction is also possible in nature. So taking another example, say proton and anti-neutron, giving pi plus pi neutral. Now, baryon number before, what we have here is 1 plus 1. For neutron, it is -1. Okay, for pi plus, it is 0. For pi 0, it is 0. So what can we see here? We can see here that the baryon number is conserved. The total number of baryons in the left-hand side is equal to the total number on the right side. Both are equal to 0. So this reaction can also occur in nature. Now let's take another example. Say proton plus neutron and giving us pi plus pi neutral. Now we have to check whether this reaction is possible in nature or not. Now, what can we go? We can go with the baryon number. Here we have +1, here we have +1, and here we have 0, here we have 0. So we can see that the baryon number is not conserved. Now, if the baryon number is not conserved, so I should say here that this reaction is not possible. This reaction is not possible.